So, Jai Hind everyone. This is Dr. Avdesh Gupta, and today we will discuss some good concept or some important concept of relational algebra. So, the query languages. Basically, various types of query languages we are using in DBMS like SQL, relational algebra, TRC, DRC. So, here we will discuss about the relational algebra only. The query language basically specifies how to access the data from the given database or given tables. The database is a collection of tables that are interrelated to each other. Different types of query languages are there, declarative and procedural. Declarative query languages is those where we can specify what data we have to retrieve, what not, how to retrieve it. And what is procedural? If we want to retrieve the data, how do we retrieve the data? We have to write the query for that related database. The query language often including updating, deletion and all and other modification of the data as well. This also called data manipulation language, DML. So this is relational algebra. Basically it is a procedural query language. It basically comprises the relational algebraic operations. Basically relational algebra take one or two relation as an input. The relation is in terms of tables or database, and it is produce a relational as an output. It produce a output in the form of table. The relation expressions or operations can be composed together. Each operation produces a relation, and a query is a very simple relational algebraic expression. 6 fundamental relational operations are there. So we will discuss 6 fundamental relational operations. Okay. So why it is so useful? Basically, each language or each expression will be useful for different types of purposes. Like SQL is a loosely based on relational algebra. SQL much more on the declarative end of the spectrum. Many relational database uses relational algebra operation for representing executing plans. Simple, clean, effective abstraction for representing how results will be generated. So basically, these are the 6 fundamental operations. The sigma operations, pi operation, we are saying projection operation, set intersection, set union, set difference, Cartesian product and rename operations. So we will discuss these 6 fundamental operations here. So the first discuss the selection operation. The selection operation will be denoted as sigma. Sigma P from the relation R. P is the predicate for the selection. Predicate. P refers to the attribute in the relation R, but no other relation. So we can use some algebraic or some relation, some expressions along with this selection operations. These and these are the. We can use these. R is the input relation, so we can do it as, like for example, this is a table, or we can say this is the relation R. We have to retrieve all tuples for account in the Los Angeles branch. So how can we write it? We write selection, select the branch name is equal to Los Angeles from the account R. So this is R relation and this is predicate. Okay. So retrieve all the tuples of account in the Los Angeles branch with a balance under 300. So how can we write it? We write it branch name is equal to Los Angeles. And because in this query, we have asked that retrieve in the Los Angeles branch with a balance of. So we have to write AND operator. Balance is less than 300 and the from relation account. So this is how we can write the relation algebraic query. Okay. So this is the projection operation. Second operation, projection. What is the difference between selection and projection? Basically, selection is used to identify some rows, some tuples. But in projection of operations, we have to find some columns. If we focus on some column, like for example, if I am asking, that what is the name of a person who are living in city Ghaziabad. So we have to find the name of that particular column. So in a projection, in a selection operations, all the tables, all the columns, all the field of that particular relation will be identified as this. But in projection, like for example, this is a relation. So in this relation, there are three columns, and we have to find only one column. Like retrieve the branch name only, not all. We have to retrieve the branch name that have at least one account. So it means any of the branch name which have one account means the branch name has one account open in that particular branch. So projection on branch name from the relation account. So it will result this type, only this query. This is the resultant query. So in selection, where all the columns we have to find, but in projection only the focused column we have to retrieve. Okay. So set union, it is very common. It is basically the same concept which we are used in discrete mathematics as a union. It means we have to find the attribute of tuple R, or we can say relation R or relation S. If there are two relation R and S, so we have to find the combined operations of relation R and S. So this is a symbol of union, and this is the relation R and this is the relation S. There are two relations. Like for example, if there are two relations, the account and loan. There are two schema, account and loan. So what we have to do in these two accounts, we have to find, if we find the combination of these two, so we have to union this particular account with the loan, account and loan. So we have to do it. There are another more tables are there, depositor and borrower, and the question is find the name of all customer. We have to find the name of customer. It means we have to find the customer name. Have either a bank account or a loan account. Have either the bank account or loan account. If the customer has a loan account, so this is the loan account. Have the bank account, so this is the ID. So we have to find the combination of these two. So how can we do it? So this we can do it by using this projection on customer name from depositor, union of projection of customer name from borrower. So from both table we have to find the customer name. So this is the customer name from this table and from this table. So we have to combine the two relation into one relation. So set difference. Another is a set difference. This is basically, we can understand it with a minus symbol. So written as R minus S. We have to subtract the relation from R. So what is the resultant output? Suppose R has 5 tuples and S has 3 tuples. So the out of these 5 tuples, 2 tuples are common. So what we get? We get 3 tuples. The 2 tuples which are common, it will not show. But the rest of the tuples of R will be shown. So resultant content tuple that are only in R but not in S will be shown. How? Like for example, find all the customer that have an account but not a loan. So find the name of customer, the customer who have the account but not a loan. So we have to subtract who have having the loan. So how can we do it? We can do it like for example, projection on customer name from depositor relation minus projection on customer name from borrower relation. Both has some common name, like for example, Smith is the common and Lewis is the common. So other two are the extra name. So these Johnson and Reynolds, these two names will be in answer query. So this is how we can apply the set difference relation or set difference operations. Cartesian product. So Cartesian product is another important concept of relational algebra. In Cartesian product, we have to apply the multiplication of two tables. Like for example, if one table having 5 tuples, another table having 4 tuples. So what is the output in the terms of tuples? 5 into 4, 20 tuples. It means 20 tuples we are getting by using Cartesian product. We can say that this is another example of join query also. Okay. So, yes, this is the table borrower and this is the table of loan. So compute the result of borrower multiplied by loan. So we can find that loan ID is the common in both, but customer name is the independent attribute in this table, and branch name and amount are the independent attributes in this table. So if we multiply or Cartesian product of these two tables, borrower and loan. So what will we get? These 4 of borrower table and these 4 from the loan table, it will give 16 tuples. 16 tuples how? Anderson, L437, loan ID. Then 437, Las Vegas, 4300. So if we do this type of calculation, so we are getting the intersection among these two. But if we getting this into this, this into this, this into this, this into this, it means the 4 tuples of this borrower multiplied with the 4 tuples of loan will be getting another 4. It means these 4 multiplied by this gives 4 tuples. This again with this, then again 4 tuples. So we can get 16 tuples by using Cartesian product. Okay. So this is the final table. Customer name, borrower, loan ID, branch name and amount. This is how we can get the final 16 tuples of Cartesian product. Okay. So Cartesian product is very good example where we can get the combined information, or we can get maximum information about any type of tuple or any type of column. Basically, there are some examples like Cartesian product to associate related rows between 2 tables, but a lot of extra rows are included. Somehow this may again happen. So we have to remove this thing. We have to remove this thing by using some other operations. So retrieving the name of all customer with loan at the settled branch. This or this need both borrower and loan relation, correlate tuples in the relation using loan ID, and then computing result is very easy. If we do in this way, we can find the good number of tuples. It means lesser number of tuples in the resultant table. So we can avoid doing Cartesian product initially. So we have to find some concrete or some abstract results from each and every table. Then we have to apply the Cartesian product. Associate customer name with a loan detail using Cartesian product and a select. So what we have to do? Select borrower loan is equal to loan dot loan ID borrower into loan. So there are also 2 tables are multiplying each other, but how? Where the loan borrower loan and the loan dot loan, who have the loan as a borrower and who has the loan from a loan account. If these 2 loan ID are equal, then only the borrower and loan table will multiply. So this can create a lower number of tuples in the resultant table. Okay. Rename operation. Rename operation is very common operation and it is used very minimally used, because rename operation is generally what it has to do. It just rename the tuple, rename the relation name. For example, result of relation operations are unnamed. For example, if we are writing a query and we are extracting some database, the resultant table, it do not have any name. So what we have to do? We have to give some name to the resultant query. So we can give the name. We can give the result a name using the rename operator. Like for example, this is a row E. So Greek row, not lowercase. This is P. Okay. So E is an expression that produces a relation, and E can be named relation or a name variable. Okay. So most general form is row A1, A2, A2, AN and then E. Allow renaming of relation attributes and requirement E as the arity N. Okay. So scope of rename operation. We can renaming the tuple, we can renaming the attribute name, we can renaming a relation name, anything. This does not create a new relation variable, but it automatically renaming the tuple, attribute name or the relation rename. Rename operator basically it is used for 2 main purposes. The first purpose is to allow a derived relation and its attribute to be referred by enclosing relational algebra. Like for example, what is derived attribute? If I am giving you the date of birth of a candidate and I am asking what is the age of that particular person, so what you have to do? You have to do the current date minus his date of birth. So you can get how many years, how many months, how many days he have. He is his age we can find out. So this particular thing is a derived attribute. So we are not having the any function just to name that this derived attribute. So we have this function to rename this derived attribute. So this is the derived attribute from, if we getting the age from the date of birth, we can extract the age of the particular person and we can give the name by using this rename operator. Another function is it allow a base relation to be used multiple way in a query. Like for example, in this way, this is a relation and this is a rename operation. In other words, rename operation is used to resolve ambiguities with a specific relation expressions. Rename examples. Find the ID of the loan with the largest amount. So this is the largest amount, and find the ID. How to find the loan with the largest amount? At least with the tool we have so far, much easier to find the loan we have smaller than some other loan. Then use set difference to find the largest amount. We can do it in this way. But how to find the loan with an amount smaller than the some other loan? So if this is 7,500 and we have to find second largest. So if we have to find this one, 4300, how can we find it? So this is use Cartesian product loan by itself and compare each loan amount with the other loan. And the problem is can't distinguish between attribute of left and right relation. And the solution is by very simple, use rename operation with the loan and rename of next loan. Now right relation is named as a test because we have renaming already the right relation as a test. So right relation will be renamed as test. So this is the best case of a rename operation. Find ID of loan with an amount smaller than the some other loan. So this is also we can do it. Projection on loan from loan ID and projection on loan amount is less than test amount, what we have get in the previous operations. Then loan and test loan, the new relation will be renamed as test. And finally, we can get our result, projection on loan and loan minus this one. Okay, so this we can get L421, L421, this we can get. Okay, so what if multiple loan have maximum value? All loans with maximum value appear in a result. For example, if this particular loan ID has the same loan amount, so what we get? We get this, if other loan ID has the same loan amount, then other loan ID also displayed in this result. These are the some additional relation operations: set intersection, natural join, division, and assignment. So this is set intersection. Set intersection is basically understood in a way that if we are identifying the common attributes between two relations, this is the intersection in the same way as we are doing in discrete mathematics. So this is R intersection S, can be better understood R minus S. Okay. So next is natural join. Natural join is very popular because this join operation is somehow related to Cartesian product also. So most common of Cartesian product is to correlate tuple with the same key value, which is called as a join operation. And the natural join is a shorthand of the operation, is written as this join. So R join S. So R and S must have some common attribute, at least one common attribute. The common attribute usually a key for R or S. Okay. So by using this particular key, we can find the relation between R and S. So there are two relations, R and S, there are two relations. So attribute used to perform a natural join in such a way that R intersection S is equals to a set of A1 to AN. And the formal definition is R projection R join S is equal to projection on R union S, and this selection of R dot A, S dot A, intersection of R dot A, S dot A, intersection of, and so on, R cross S. So R and S are joining using the equal condition based on their common attribute, because both table have some common attribute. So result is projected so that common attribute only appears one. Natural join. Find the name of all customer with a loan. The result is projection on customer name and the selection of borrower dot loan ID is equal to loan dot loan ID, because this particular loan ID is the common from borrower and loan, and the borrower and loan will be Cartesian product, and this can be rewritten with the natural join in this way: projection of customer name, borrower borrower join natural join loan. So this is another example of natural join. We can replace this query by using this query. It is very common to compute the join across multiple table. We can join in not in between two tables. We can join in more than two tables also. Like for example, if we have to join customer table with borrower table with loan table, so we can apply this join operation between or among these relations. Natural join operation is also associative. Like for example, borrower loan is equivalent to customer join borrower join loan customer. So in this way we can do it also. Division operation. Division operation is like in the for example, if we are dividing the S by R, so this is a division operation. It is in the same way like we are doing set difference R minus S or R division S. We can get different operations, we can do different output, but this is in the same way like we are doing set difference. So to understand this particular, we have to search one thing, puzzle database. From the puzzle database we can get it very easily. So this is a division operation that we can divide S by R. So required S is a subset of R. All attributes of S must also be in R. So result has a schema R minus S. Every tuple T in result satisfy these conditions. So this is the tuple relation calculus. So this condition must be satisfied. Okay. So this is the division not provided natively a most SQL databases, which is basically really needed and easy enough to implement in SQL if needed. So these all about the relational algebra. This is the assignment operator. Assignment operator is just to assign the right hand side query or right hand side the answers into the left hand side variable. Like for example, if we assign some relational algebraic query answers into some variable, so this is a assignment operator. We can assign the value of this into the left hand side operator. So left hand side variable. So this is the assignment operator we can apply in relational algebra. Okay. So this is all about the relational algebra. Thank you very much.